Gravity might be nothing but a cosmic illusion. For over a century, two pillars of physics have stood in perfect contradiction. Quantum mechanics rules the impossibly small, a world of probability and particles. General relativity governs the vast cosmos, where gravity is the curvature of spacetime itself. Yet these two masterpieces cannot be reconciled, and where they clash, at the hearts of black holes and the first instant of the Big Bang, our understanding of reality breaks down completely. Solving this is the final grand challenge, the quest for a theory of quantum gravity. By the end of this exploration, you will have a panoramic view of 30 distinct visions for the deepest layer of reality, from established frameworks to ideas that border on philosophy. We will see how some theories suggest space is woven from tiny loops, while others propose our universe is a holographic projection. What single idea feels most true to the strange nature of our cosmos? The first and perhaps most radical idea on our journey suggests that space itself has a structure. This is loop quantum gravity, a theory that boldly declares the smooth, continuous backdrop of our universe is an illusion. Think of the fabric of reality not as a blank sheet, but as a vast, intricate tapestry. In this view, space is woven from an unimaginably dense network of tiny, vibrating loops. These are the fundamental atoms of geometry, the smallest possible pieces of space. There is no smaller than this scale, no infinite divisibility, just as you cannot cut an atom of gold in half and still have gold. Gravity, then, is not a force traveling through space, but the dynamic behavior of this woven cosmic fabric, the way these loops twist, link, and interact with one another. To visualize this, physicists use diagrams called spin networks, a breathtakingly complex web of connections that define the very volume and geometry of everything around you. At this quantum level, spacetime becomes a churning, foamy structure, constantly fluctuating. This leads to one of the theory's most profound predictions. If we rewind time to the moment of the Big Bang, the density of matter and energy would become so immense that these quantum loops of space would be stretched to their limit. But instead of collapsing into an infinitely dense, nonsensical point, loop quantum gravity suggests they would reach a maximum tension and then rebound. The result, not a cataclysmic beginning from nothing, but a great cosmic bounce. Our universe may have been born from the collapse of a previous cosmos, an eternal cycle of contraction and expansion written into the quantum code of space itself. This radical reimagining of space has direct, testable consequences for the most violent places in existence. Inside a black hole, where general relativity predicts an infinitely dense point of no return called a singularity, loop quantum gravity offers a different fate. The weave of quantum loops cannot be compressed forever. As matter collapses inward, the loops of space reach a maximum density and then repel, creating a powerful quantum bounce. The result could be a bridge to another region of spacetime, a theoretical exit from the black hole known as a white hole, or perhaps the birth of an entirely new universe within the collapse. The same principle applies to our cosmic origin. The Big Bang singularity is replaced by a big bounce, a transition from a previous contracting phase into our expanding one. Our universe, then, may not be a one-time event, but one link in an endless cosmic chain. This quantum geometry could also leave fingerprints on the oldest light in the sky. If spacetime is a churning quantum foam at the tiniest scales, then light traveling across billions of light years might be subtly affected. Different colors or wavelengths of light could travel at minutely different speeds through this foamy structure. It would be like a swimmer moving through choppy water versus calm water, their progress slightly altered by the texture of the medium. While this effect would be incredibly small, astronomers are searching for it in the light from distant gamma-ray bursts and quasars, hunting for any hint that the vacuum of space has a grain. Yet for all its elegant geometry, loop quantum gravity faces profound challenges. Its mathematics describe a beautiful, pure quantum space, but incorporating the messy particles and forces of our universe, the matter fields, has proven intensely difficult. How do electrons and quarks emerge from a dance of loops? Furthermore, the smooth, classical spacetime we all experience must somehow emerge from this frenetic quantum foam, a process called decoherence that is not yet fully understood. The theory lies in a realm of profound abstraction, and bridging that gap to the tangible world we measure remains its greatest hurdle. Where one theory seeks to quantize the very stage of reality, another suggests the stage itself is not fundamental. While one approach rebuilds space from loops, another reimagines the very nature of matter and energy. String theory proposes that the fundamental ingredients of the cosmos are not point-like particles, but unimaginably tiny, vibrating strings. An electron is not a zero-dimensional dot, but a string vibrating in one specific pattern. A quark is the same type of string, just humming a different harmonic note. In this symphony of reality, every particle and every force is a distinct vibration on these cosmic strings. This elegant idea provides a stunning solution to the gravity problem. Among the possible vibrations, there is one special pattern that behaves exactly like the theoretical particle of gravity, the graviton. It is a closed loop of string, and its properties force it to interact in a way that perfectly reproduces Einstein's equations of general relativity. Gravity is no longer an outsider, it is simply another note in the universal chord, woven into the theory's fabric from the very beginning. Yet this beautiful harmony comes at a strange and magnificent cost. The mathematics of string theory only works if the universe has more than the 3 spatial dimensions we know. It requires either 10 or 11 dimensions in total. Where are these extra dimensions? They are not vast, empty expanses we could travel through. Instead, they are curled up or compactified into shapes so incredibly small that they escape all notice, existing at every single point in our familiar 3-dimensional space. To picture this, think of a long, thin garden hose. From a great distance, it looks like a simple 1-dimensional line, but up close, you see it has a circular 2-dimensional surface. Our reality could be similar, with 6 or 7 extra dimensions curled into complex geometric shapes called Calabi-Yau manifolds. The specific way these dimensions are folded determines the laws of physics in our visible universe, from the strength of gravity to the masses of particles. This leads to a profound and controversial implication known as the string theory landscape. There may not be one unique solution, but an astronomically vast number of possible ways for these extra dimensions to curl up. Each configuration creates a universe with different physical constants. Ours, with its specific laws allowing for stars, planets, and life, would be just one possibility in a near-infinite cosmic array. The dream of a single, elegant equation describing everything may give way to a multiverse of possibilities, where the answer to why our laws are what they are is simply because here, in this pocket of reality, they are. The landscape of string theory presents a dizzying philosophical dilemma. If there are 10 to the 500 possible ways for the extra dimensions to curl up, each creating a universe with unique laws, then our cosmos is not special. It is simply one possibility that happened to emerge, with constants fine-tuned for complexity by chance. This vast array of possibilities is the string theory multiverse, and it transforms a question of physics into one of cosmic anthropology. Why are the laws of nature just right for life? In this view, the answer is startlingly simple, because in an incomprehensibly vast ensemble of universes, some will, by pure statistical luck, have the right conditions. We find ourselves in one of those lucky ones because we could not exist anywhere else. This is the anthropic principle applied on a cosmic scale, and for many, it feels like a retreat from explanation. It suggests that some of the most profound features of our reality may not have a deeper cause, but are merely environmental accidents, This leads directly to a more unified but even more mysterious framework, M-theory. Originally, there were 5 distinct versions of string theory, each with different types of strings and dimensional requirements. In the 1990s, physicists discovered that these 5 theories were not competitors, but different faces of a single, deeper structure. Much like viewing a cube from different angles reveals different shapes. This overarching structure is M-theory, existing in 11 dimensions. The M stands for membrane, magic, or mystery, depending on whom you ask. In M-theory, the fundamental objects are not just one-dimensional strings, but also two-dimensional membranes, three-dimensional blobs, and higher-dimensional objects collectively called branes. Our entire universe could be a three-dimensional brane floating in a higher-dimensional bulk space, with gravity perhaps leaking between branes. This vision is grand and mathematically compelling, but it amplifies the central controversy surrounding all these ideas, the crisis of testability. A scientific theory must make predictions that can be falsified by experiment. Yet the energy scales required to probe strings or the compactified dimensions are far beyond any particle accelerator we could ever build. The multiverse concept, by predicting that every possible set of laws exists somewhere, seems to predict everything and therefore nothing specific about our own universe. Does this mean the quest for quantum gravity has strayed from science into the realm of mathematical philosophy? Proponents argue that indirect evidence, like the discovery of supersymmetry at a collider or specific patterns in the cosmic microwave background, could support the framework. Critics contend that without a clear, unique prediction for our observable world, the theory resides in a troubling limbo. It is a magnificent castle in the air, built from the most beautiful mathematics physicists have ever devised, but its foundations cannot yet be touched by experiment. This tension defines the modern search for quantum gravity, a struggle between mathematical elegance and empirical grounding. Where does reality ultimately reside, in the equations or in the data? But what if we could watch spacetime itself evolve from its most basic ingredients? Causal dynamical triangulations offers exactly that, a digital laboratory where the universe is built piece by piece. Forget strings or loops for a moment. This theory uses the simplest geometric shapes imaginable, tiny triangles, and their higher dimensional cousins called simplices. Think of them as the cosmic Lego blocks of reality. In this approach, physicists do not start with complex equations. They start with a massive pile of these blocks and a single, crucial rule: causality. Every connection between blocks must respect the flow of time, ensuring cause always precedes effect. With this rule in place, they let a powerful computer randomly assemble these blocks into a vast, churning foam. This is the quantum gravitational vacuum, a seething, chaotic mess with no recognizable structure. Then, something remarkable happens. As the simulation runs, averaging over all the possible random configurations that obey causality, a stable, large-scale order begins to crystallize from the chaos. The frenetic, jumbled foam spontaneously gives rise to a smooth, four-dimensional universe, precisely 3 dimensions of space and 1 of time, exactly as we experience. It is a phased transition of geometry, akin to watching individual water molecules suddenly lock into the perfect, crystalline structure of an ice cube. The success of these simulations is breathtaking. From fundamentally lower-dimensional, random building blocks, our familiar macroscopic reality emerges all on its own. This suggests that the 4-dimensional continuum described by Einstein may not be a fundamental truth, but a collective illusion, a statistical average of countless quantum fluctuations. The smooth stage of spacetime is not the starting point, it is the destination. While causal dynamical triangulations provides a stunning proof of concept, it is, for now, a universe in a box. The simulations show that a 4-dimensional classical world can emerge, but they have not yet successfully incorporated the full richness of the standard model particles and forces. The challenge is to go from building the stage to populating it with actors. Yet its core lesson is profound. The geometry of our cosmos may be an inevitable outcome of simple rules played out on a quantum scale. Where one digital approach builds from triangles, another asks if the entire universe is made of information. Information is the most fundamental currency of reality. This is the radical premise of the fourth major approach, a concept that shifts the focus from what things are to what they know. Asymptotic safety in quantum gravity asks a deceptively simple question. What if gravity is not a force to be quantized, but a pattern of information that becomes predictable at its most extreme energies? To understand this, we need to think about how physicists tame infinity. In the quantum world, when you try to calculate the interactions of particles, you often get nonsensical, infinite answers. For forces like electromagnetism, a mathematical technique called renormalization sweeps these infinities under the rug, allowing for precise, finite predictions. For decades, gravity stubbornly resisted this fix. Every attempt to apply the same quantum rules to Einstein's equations produced an unstoppable avalanche of infinities, making calculations impossible. This was the central roadblock. Asymptotic safety proposes a brilliant escape route. Imagine you are following a river to its source. In most quantum theories, as you go to higher energies, the strength of the interaction, the river's current, becomes wilder and more unpredictable until it cascades into an infinite waterfall. But what if, just at the point where you expect chaos, the river flows into a serene, stable lake? In the language of physics, this lake is called a non-trivial ultraviolet fixed point. Ultraviolet refers to the high-energy, short-distance realm where quantum gravity reigns. Fixed point means the theory's behavior settles into a predictable, finite pattern. The word asymptotic means you approach this safe point without ever quite reaching it, like a curve that gets closer and closer to a line but never touches it. If gravity possesses this fixed point, then at the extreme energies near the Big Bang or inside a black hole, the theory does not blow up. It becomes well-behaved or safe. The infinities are not removed, they are rendered harmless by the theory's own inherent structure. This is not a trick, it is a property of the mathematics of spacetime itself. The promise of this idea is immense. Unlike string theory, it does not require extra dimensions or unseen supersymmetric particles. It works directly with the four-dimensional spacetime we know, using the established tools of quantum field theory. It suggests that the theory of gravity we already use, Einstein's general relativity, is not wrong. It is what physicists call an effective field theory, a brilliant and accurate description that works perfectly at everyday energies like the physics of a flowing river. But just as water is actually made of molecules, the effective theory hints at a deeper quantum structure. Asymptotic safety aims to be that deeper theory, the molecular description of spacetime, which seamlessly connects to Einstein's equations at lower energies. Researchers use powerful supercomputers to map the mathematical landscape of this theory, searching for that stable fixed point. Evidence suggests it might be there. If it is, it would mean that gravity, alone among the forces, has this unique self-taming property. It would be a universe where the fabric of reality possesses a kind of built-in resilience, preventing its own equations from self-destructing at the moment of creation. The theory could then make concrete predictions, perhaps about the behavior of spacetime foam or the final stages of black hole evaporation. Predictions that future gravitational wave observatories or studies of the cosmic microwave background might one day test. It offers a path where the dream of quantum gravity remains rooted in the familiar soil of four dimensions, waiting for its moment of validation. The smooth stage of spacetime may be an illusion, but could the force that holds us to it be one as well? This is the startling claim of entropic gravity, a theory that turns our understanding of the cosmos inside out. Proposed by physicist Eric Verland, this idea suggests gravity is not a fundamental force of nature at all. It is not woven into the fabric of the universe like electromagnetism. Instead, gravity emerges much like the concept of temperature. Think about a hot cup of coffee. Temperature is not a fundamental property of any single molecule. It is a collective effect, a statistical average of the frantic motion of trillions of molecules. In the same way, Verland proposes that gravity is an entropic force, a side effect of a deeper, more fundamental process, the relentless drive of the universe toward disorder or higher entropy. At its heart, this theory is about information. The holographic principle, which we touched on earlier, suggests all the information describing a volume of space can be encoded on its two-dimensional boundary, like a cosmic DVD. Verland takes this a step further. He imagines that what we perceive as space is filled with invisible holographic screens. When a particle, like an atom, approaches one of these screens, it changes the amount of information stored there. The drive of the universe to maximize entropy then causes the screen to react, pushing the particle in a specific direction. That push, that tendency to move toward higher entropy, is what we feel as gravity. It is not an attraction between masses, but a statistical tendency arising from the way information is rearranged on the boundary of our reality. This leads to one of the theory's most provocative implications, a new explanation for dark matter. For decades, astronomers have observed galaxies spinning so fast that the visible stars and gas should fly apart, unless there is a huge amount of unseen dark matter holding them together with its gravity. But what if that extra gravity is not from invisible particles? Entropic gravity suggests that in the deep, sparse gravitational fields at the edges of galaxies, the emergent nature of gravity itself changes. The equations predict an additional gravitational effect that perfectly mimics the presence of dark matter without requiring a single new, undiscovered particle. It would mean dark matter is not a substance but a shadow, an artifact of gravity behaving differently on cosmic scales than Newton or Einstein predicted. This radical proposal has ignited fierce debate. Supporters see it as a profound unification, linking gravity, thermodynamics, and quantum information in an elegant new framework. Critics argue the theory is still incomplete, lacking the precise mathematical machinery to make testable predictions that clearly distinguish it from the standard dark matter model. Yet, its very existence challenges a 400-year-old assumption: we have always searched for the source of gravity. What if we have been searching for the wrong thing entirely, and gravity is not a source but a consequence, the cosmic echo of information finding its most likely arrangement? The universe may not be a smooth, flowing river of time, but a cascade of distinct individual moments. Causal set theory embraces this radical granularity, proposing that reality at its most fundamental level is not continuous but a discrete collection of events. Think of it as the cosmic equivalent of a pointillist painting. Up close, you see only individual dots, distinct and separate, but from a distance, those dots blend into a seamless, beautiful image of spacetime. In this theory, the dots are the basic elements of reality called events, and the only fundamental properties they possess are two: a causal relationship to one another and a number. This is captured in the theory's elegant slogan, order plus number equals geometry. The order refers to the causal structure, which event precedes another. This creates a vast cosmic web of cause and effect, a skeleton of before and after. The number is simply how many events exist within a given region of this web. Astonishingly, the theory proposes that from this sparse data, nothing more than a list of points and their causal connections, the full, rich geometry of spacetime, its curvature and dimensionality must emerge. It is a breathtakingly minimalist vision, building everything from almost nothing. This discreteness introduces a natural minimal length scale, often associated with the Planck length. There is no meaning to distances smaller than this because there are no events to measure between. This built-in granularity offers a powerful escape from the singularities that plague classical physics. A black hole singularity is not an infinitely dense point, but simply a region where the causal set becomes so dense that our classical notion of smooth spacetime breaks down. The Big Bang is not a beginning from nothing, but the first event in the causal chain with no predecessor. Yet this beautiful simplicity faces a monumental challenge: the recovery of Lorentz invariance. This is a cornerstone of Einstein's relativity, stating that the laws of physics are the same for all observers moving at constant velocity. In a smooth, continuous spacetime, this works perfectly. But in a discrete causal set where points have a minimum separation, there is a danger that a moving observer would see this granular structure, like noticing the pixels on a screen if you could get close enough, violating the principle that all inertial frames are equal. The great hope is that this discrete grain will be hidden by the random, statistical nature of the set, just as you cannot discern the individual atoms in a glass of water by looking at it. The underlying lattice may exist, but its effects average out to produce the smooth, relativistic spacetime we all experience. Proving this remains one of the theory's central tasks, a puzzle where the quantum nature of reality must conspire to hide its own discrete skeleton from our view. Coordinates themselves may be fundamentally uncertain. This is the startling premise of non-commutative geometry, a theory that proposes the very stage of reality has a built-in quantum fuzziness. In our everyday world and in Einstein's relativity, we can specify a location with precise coordinates, like a street address for the universe. We assume that measuring an object's position along the east-west axis has no effect on our ability to measure its position along the north-south axis. The order of measurement does not matter, the coordinates commute. But in the quantum realm, this certainty breaks down for properties like position and momentum. You cannot know both with absolute precision. The more you pin down one, the more the other blurs. Non-commutative geometry applies this same quantum principle to spacetime itself. At the unimaginably tiny Planck scale, the theory suggests that the coordinates of space no longer commute. Measuring a location in one direction fundamentally disturbs or makes fuzzy the measurement in a perpendicular direction. It is as if the universe's grid lines become smeared, and the very concept of a sharp, distinct point in space loses all meaning. Space becomes inherently granular and uncertain, a quantum foam not of loops or triangles but of blurred geometry. The mathematical language for this comes from the work of French mathematician Alain Connes. He developed a powerful reformulation of geometry that does not rely on points or distances in the usual sense. Instead, geometry is described by abstract algebraic relationships, by how mathematical objects interact with one another. In this framework, the classical, smooth spacetime of general relativity is just a special, simple case. The more general and potentially more true description is a non-commutative space where geometry is defined by a kind of quantum algebra. This is not just a mathematical curiosity, it has a breathtaking potential consequence. The forces and particles of the Standard Model, which appear so separate from gravity in our current theories, may find a purely geometric origin within this fuzzy spacetime. Connes and his collaborators have shown that the entire elaborate structure of the Standard Model, with its quarks, leptons, Higgs boson, and force carriers, can be derived naturally from the spectral properties of a specific non-commutative space. In this vision, an electron is not a particle moving through space, it is a vibrational mode of the geometry itself, a note in the chord of a quantized cosmos. All forces, including gravity, become different manifestations of the same underlying geometric truth. The dream of unification is thus recast, not as tying together different pieces of string, but as recognizing that what we call particles and forces are merely shadows cast by the deep, non-commutative shape of reality. The challenge, as with so many of these ideas, is experimental. The non-commutative fuzziness is expected to appear only at the Planck scale, far beyond direct probing. Yet, some models predict subtle effects that might be amplified in extreme astrophysical environments, like the way light from distant gamma-ray bursts could carry an imprint of this spacetime grain. It is a theory of profound elegance, suggesting that when we finally peer into the heart of quantum gravity, we may not find loops, strings, or pixels, but a beautiful, blurred algebra from which everything we know simply crystallizes. What if time itself is not what we think it is? One of the most sacred principles in modern physics is Lorentz invariance, the idea that the laws of nature and the speed of light remain constant for all observers. This symmetry between space and time is the bedrock of Einstein's relativity. But one daring theory asks, what if this symmetry is not fundamental, but merely an emergent feature of our low-energy world? This is Horava Lifshitz gravity, a proposal that breaks the deepest taboo by treating time and space differently at the most fundamental level. The motivation is starkly practical, to finally make gravity renormalizable, to tame those destructive infinities that have blocked the quantization of gravity for generations. The theory achieves this by giving time a privileged role. At extremely high energies near the Big Bang, time behaves differently from the three dimensions of space. It is as if the universe has a preferred clock, a master foliation of moments that slices through reality, providing a universal standard of before and after. This special status for time radically simplifies the equations, allowing physicists to apply the standard techniques of quantum field theory and, crucially, to get finite, sensible answers. The potential payoffs are immense. This modified framework of gravity could naturally drive a period of rapid cosmic inflation in the early universe, solving long-standing puzzles about the uniformity and flatness of the cosmos. More strikingly, it might offer a new explanation for dark matter. Certain versions of the theory predict new, long-range forces or exotic gravitational effects that could mimic the presence of unseen mass, all without requiring a new, undiscovered particle. Yet this radical power comes at a profound cost. The deliberate breaking of Lorentz invariance flies in the face of over a century of exquisitely precise experiments. From particle accelerators to observations of distant starlight, every test has confirmed that Lorentz symmetry holds to an incredible degree of accuracy. If Horava Lifshitz gravity is correct, then these high-energy violations must be hidden from our current view, smoothed away as the universe cooled. Critics argue that introducing such a fundamental asymmetry is too high a price to pay, a step backward from the beautiful democratic principles of relativity. It is a theory born from pragmatism, willing to sacrifice a cherished symmetry for the chance of mathematical control, leaving us to wonder if our deepest intuitions about time are merely a comforting illusion of our calm, low-energy corner of the cosmos. Spacetime may not be the fundamental arena. Roger Penrose's twistor theory proposes a stunning inversion where the points of space and time are not the building blocks but secondary constructions. In this view, the true primary elements are twistors, enigmatic objects that exist in a complex space of their own. A twistor is not a point in our universe. It is more like a complete description of a light ray, encoding both its direction and its quantum spin. The magic lies in the fact that if you gather a family of these twistors, the points where their corresponding light rays intersect define a location in space-time. Our familiar four-dimensional continuum emerges from a web of relationships in this more fundamental twistor space. It is a profound shift in perspective, like realizing that a city is not defined by its street addresses, but by the entire network of journeys people take between them. This framework holds immense promise for simplifying the notoriously complex mathematics of particle interactions. Calculating how particles scatter in quantum field theory often requires pages of intricate algebra. In twistor space, these same calculations can become elegantly geometric, sometimes reducing to a single, beautiful diagram. More importantly, because twistors inherently blend concepts of quantum spin with geometry, the theory offers a path to describing gravity in a way that is quantum mechanical from its very conception. There is no need to quantize a classical theory. The quantum nature is baked into the ingredients. For decades, twistor theory lived as a brilliant but somewhat isolated mathematical structure, admired for its beauty but struggling to fully reproduce the physics of Einstein's gravity. However, recent developments have sparked a renaissance. Connections to string theory, particularly through a discovery known as the amplitude revolution, have shown that twistor methods are incredibly powerful for calculating particle scattering amplitudes. This cross-pollination has breathed new life into the field, suggesting twistors may provide the perfect language for certain aspects of a final theory, even if not the entire foundation. Its current status is that of a deeply insightful map, one that reveals stunningly simple routes through territories we once thought were impenetrably complex. The full journey from twistor space to the tangible, dynamic universe of stars and planets remains an active quest, a search for the code that translates this exquisite mathematical poetry into the prose of physical law. The bubbling quantum foam of geometry demands a language for its collective roar. Group field theory provides exactly that, a second quantization of spacetime itself. To grasp this, think of the difference between describing a single water molecule and the ocean as a whole. The first is quantum mechanics, the second is quantum field theory, which treats particles as excited states of an underlying field. Group field theory applies this same powerful leap to the very atoms of space. Its fundamental entities are not points or loops, but abstract fields defined on mathematical groups, the same structures that describe rotations and symmetries. In this view, a single quantum of space, like a tiny tetrahedron from the spin foam approach, is an excitation of this cosmic field. The field exists everywhere and nowhere, a sea of potential geometry. Spacetime as we know it, with its smooth continuity and definite shape, is not the starting point. It is a phase that emerges when these abstract field excitations undergo a process of condensation, locking together into a coherent pattern. It is like watching a crystal suddenly form from a supercooled liquid, a dramatic shift from disorder to a rigid, ordered structure. Our universe may have begun not with a bang, but with a freeze, a geometric phase transition where the quantum gravitational field crystallized into the four-dimensional stage we now inhabit. This framework is deeply intertwined with loop quantum gravity and spin foams, providing the necessary machinery to describe not just individual quanta of space, but how they interact, combine, and collectively behave as a dynamic whole. It turns the static spin foam diagrams into a living, breathing quantum field theory of geometry, where spacetime itself can ripple, flow, and evolve according to quantum rules. The visual is one of a seething, bubbling foam, but a foam where each bubble is a quantum of geometry, constantly interacting, merging, and splitting. From this frenetic, pre-geometric soup, the calm order of classical spacetime must somehow precipitate. The great challenge for group field theory is to show precisely how this condensation happens and to prove that the resulting crystalline structure inevitably looks like our expanding, relativistic universe. It is a search for the cosmic recipe that transforms quantum chaos into cosmic order, asking if the laws of physics themselves are frozen music, a stable pattern etched into the condensing field of reality. The universe may be a cosmic mirage, a stunning projection from a simpler, lower-dimensional reality. This is the holographic principle, perhaps the most radical and well-supported idea in the quest for quantum gravity. Its origin lies in the paradoxical nature of black holes. When matter falls into a black hole, it seems to vanish, taking all its information with it, which violates a sacred quantum rule that information can never be destroyed. In the 1970s, physicist Jacob Bekenstein made a startling proposal. A black hole's entropy, which is a measure of its hidden information, is not proportional to its volume, but to the area of its event horizon, its two-dimensional surface. Stephen Hawking later showed black holes radiate heat and evaporate, making this information paradox even more acute. Where does the information go? The holographic principle offers a breathtaking answer. It never falls in because it was never truly inside to begin with. All the information that describes everything within a three-dimensional volume, every star, every planet, every person, is perfectly encoded on the two-dimensional boundary enclosing it, like a fantastically complex tattoo on a spherical shell. Our experience of a three-dimensional world is a magnificent illusion, a holographic projection from that encoded data. This is not just philosophy. It has a precise mathematical realization in string theory known as the anti-de Sitter conformal field theory correspondence, or AD-SCFT. It proposes a perfect duality, a complete dictionary between a theory of gravity operating in a warped, higher-dimensional space and a quantum field theory without gravity living on its lower-dimensional boundary. A complex gravitational event inside the volume, like two black holes colliding, is exactly equivalent to a specific, intricate calculation involving particles and forces on the flat boundary. One of the most profound implications is a challenge to our most basic intuition, locality. In our world, things interact by being close together, but on the holographic screen, all the information is smeared together. 2 points that seem far apart in our three-dimensional projection might be adjacent entries in the two-dimensional code. What we perceive as a force acting across space could be a local interaction in the underlying theory. This principle redefines dimensionality itself, suggesting that the three spatial dimensions we move through are not fundamental, but emergent properties of how information is organized and processed. We are, in a very real sense, living inside a cosmic simulation, with the laws of physics as the rendering software for a universe whose true source code is written on a distant, two-dimensional surface. The holographic universe is a breathtaking idea, but what if that two-dimensional screen itself has a history, a moment of creation from something even stranger? Quantum gravity proposes exactly that, a model where space is not born smooth, but as a chaotic, hyper-connected network. In this vision, the fundamental ingredients of reality are not particles or strings, but simple nodes like dots on a page. In the searing heat of the earliest moments, every single node was connected to every other node. The universe was a complete graph, a buzzing, frenzied network where every point was adjacent to all others. There was no distance, no far away, because everything was directly linked. In this state, the very concepts of dimension and locality had no meaning. It was a boiling soup of pure connection. Then, as the cosmos expanded and cooled, a cosmic freeze-out began. Just as water molecules lock into place as ice, the links between these nodes began to freeze and break. Connections that once hummed with energy suddenly went dark, turning off. This process was not random. It followed a rule of minimizing energy, leading to a specific, stable pattern. As more and more links froze, the densely connected graph began to thin out. From the primordial chaos, a sparse, orderly lattice emerged. In most regions, nodes ended up connected only to a handful of their nearest neighbors, spontaneously generating a structure with 3 dimensions. Our familiar, local, three-dimensional space is not assumed. It is the frozen relic of a great cosmic chilling, a specific pattern of broken links in an ancient graph. This phase transition from a hot, connected state to a cold, structured one offers a stunning new explanation for the universe's profound uniformity. The cosmic microwave background, the afterglow of the Big Bang, shows a nearly identical temperature in all directions, a fact that has long puzzled cosmologists. How did regions far beyond each other's light horizon ever come to equilibrium? In the quantum gravity model, the answer is simple. In the beginning, they were not far apart at all. In that initial, fully connected graph, every point was in direct contact with every other. Information and heat could spread instantly across the entire network. This allowed the whole infant universe to reach a uniform temperature before the Great Freeze-out locked in the structure of space itself. The uniformity we see today is not a coincidence, it is a memory, a fossilized imprint of that primal state of ultimate connection. The theory also provides a powerful new lens on quantum geometry itself. The transition from the high-energy graph to our low-dimensional space is a true phase change, akin to water becoming ice. This suggests that spacetime itself can exist in different phases, and what we call a universe is just one possible crystalline structure that can form. There might be other phases, other kinds of geometry with different numbers of dimensions or bizarre connectivity, frozen into existence under different conditions. Quantum gravity challenges us to see the vacuum not as empty nothingness, but as a highly ordered, low-temperature state of a deeper quantum substance. The space between stars is not passive, it is a frozen graph, and the speed of light, the ultimate limit, may simply be the rate at which information can hop from one node to the next across this now rigid lattice. It is a vision where geometry is not fundamental physics, but condensed matter physics on the grandest possible scale. Our universe may be described by the wrong set of symmetries. Shape dynamics offers this provocative correction, an elegant reformulation of Einstein's general relativity that swaps one fundamental principle for another. In Einstein's masterpiece, the theory is invariant under spacetime diffeomorphisms, a technical way of saying the laws of physics remain the same no matter how you stretch and twist the four-dimensional continuum of spacetime itself, as long as you do it smoothly. This symmetry is powerful, but it leads directly to one of the most stubborn puzzles in quantum gravity, the problem of time. When you try to quantize general relativity, time often vanishes from the core equations, becoming a meaningless parameter, leaving physicists with a frozen, static picture of reality that cannot describe evolution or change. Shape dynamics sidesteps this entirely by choosing a different, more restrictive symmetry as its foundation, spatial conformal invariance. This principle states that the physics depends only on the shapes of things, not on their absolute sizes. Imagine a cosmic sculptor who only cares about the proportions and angles within a statue, completely indifferent to whether it is carved in miniature or on a monumental scale. In this view, the universe is described at any given instant by a pure three-dimensional geometry, a snapshot of pure shape. Time is not a pre-existing stage on which shapes change. Instead, time emerges from the sequence of these shapes, from the fact that one conformal geometry can transform into another. What we experience as the flow of seconds and years is just our perception of this relentless transformation of the cosmic shape. This trade has profound mathematical consequences. By fixing the symmetry in this way, shape dynamics produces equations that are equivalent to Einstein's in their predictions for the world we see, but are structurally simpler and more amenable to quantization. The troublesome time variable is no longer a problem to be solved because it was never a fundamental ingredient to begin with. It is a derived concept emerging from the dance of shapes, much like the concept of temperature emerges from the motion of molecules. This approach offers a fresh perspective on some of cosmology's deepest questions. For instance, it provides a natural explanation for why the universe appears so uniform on large scales, suggesting that this homogeneity is a direct consequence of the universe seeking the simplest, most uniform shape as it evolves. The promise of shape dynamics is a cleaner path to a quantum theory of gravity, one where the ghost of time does not haunt the equations. It asks us to consider that our most intimate experience, the relentless march of time, might be the grandest illusion of all, a cosmic story told not through clocks, but through an infinite sequence of shifting, timeless forms. For decades, the idea was considered a dead end, a theoretical ghost town. The foundational assumption in Einstein's relativity is that the graviton, the hypothetical quantum of gravity, is massless, just like the photon. This masslessness is what allows gravity to reach across the universe with infinite range, bending starlight and holding galaxies together. But what if that assumption is wrong? What if the graviton has a vanishingly small but non-zero mass? This is the radical proposition of massive gravity, a theory that was long dismissed as mathematically diseased. Early attempts to give the graviton a mass introduced catastrophic instabilities. Phantom modes called Boulware Desert ghosts that would allow energy to appear from nothing and vanish into nowhere, violating the core principles of physics. The theory seemed not just incorrect but fundamentally sick, doomed to inconsistency. Then, in 2010, a breakthrough. Physicists Claudia de Ram, Gregory Gabadads, and Andrew Tolley cracked the code. They constructed a specific, intricate set of mathematical terms, now known as DRGT massive gravity, that exercised the ghost. For the first time, a consistent classical theory of a massive graviton existed on paper. The achievement was monumental, proving that the idea was not inherently flawed, just fiendishly difficult to get right. The implications ripple outward. If the graviton has mass, then gravity itself would behave differently over immense distances. A massive force carrier implies a finite range, though for a tiny mass, that range could still be larger than the observable universe. More importantly, it would modify the force law at cosmic scales. This opens a tantalizing possibility that the mysterious dark energy accelerating the expansion of the cosmos might not be a strange new substance filling the vacuum. It could be an artifact of gravity itself weakening in a specific way across the vast voids between galactic superclusters, a subtle signature of the graviton's mass. Yet nature has placed this idea in a straitjacket of exquisite precision. Any mass for the graviton must be inconceivably small. Observations of gravitational waves, like those from colliding black holes detected by LIGO, provide the tightest constraints. If gravitons had even a hint of mass, different frequencies of gravitational waves would travel at slightly different speeds, dispersing like colors in a prism over their billion light-year journey. LIGO saw no such dispersion. The graviton, if it is massive, must be so light that its Compton wavelength, the scale of its quantum influence, is comparable to or larger than the entire observable universe. This makes the idea incredibly difficult to test directly, but not impossible. Future, more sensitive gravitational wave observatories could probe even finer effects, or subtle anomalies in the orbits of distant pulsars might one day reveal gravity's hidden heft. Massive gravity stands as a testament to theoretical perseverance, a ghost laid to rest, now waiting for the universe to whisper whether its most elusive force carries the faintest whisper of mass. Symmetry is the hidden language of the cosmos, and one of its most beautiful dialects is supersymmetry. This is the elegant idea that for every known particle of matter, there is a hidden force-carrying partner, and for every force particle, there is a hidden matter twin. It proposes a profound kinship between the two great families of the quantum world, fermions and bosons, weaving them into a single, symmetrical tapestry. Supergravity is the breathtaking application of this principle to the force that has always stood apart, gravity itself. It is the theory that marries supersymmetry with Einstein's general relativity, creating a framework where gravity is not an afterthought, but a central, dancing partner in the symmetry. In this vision, the graviton, the quantum of gravity, would have a superpartner, the gravitino. This particle would be a fermion, a matter particle, with a spin property that blends the characteristics of a force carrier and a matter particle. It is a stunning conceptual leap, suggesting that the force that shapes the cosmos and the matter that fills it are two sides of the same coin, linked by a deep, transformative symmetry. The mathematical beauty of supergravity is immense, and it holds a special place in the quest for unification. In fact, it emerges naturally as the low-energy limit of superstring theory, acting as a kind of bridge between the 10-dimensional world of strings and our familiar 4-dimensional reality. It shows how the intricate symmetries of the higher dimensional theory can, when the extra dimensions curl up, leave behind a specific, elegant structure in our spacetime. This structure unifies all the known forces and particles into a single mathematical picture with a grace that standard quantum field theory cannot match. For particle physicists, supergravity's most tantalizing prediction is concrete and testable: the existence of a whole new zoo of particles. Every electron would have a partner called a selectron, every quark a squark, every photon a photino. These superpartners would have similar properties to their known twins but with different spin, and crucially, they would be much heavier, which is why we have not yet seen them. Their mass would stabilize at a high energy scale, perhaps accessible to our most powerful machines. This is why the search for supersymmetry has been a primary mission for the Large Hadron Collider. Finding just one of these superpartners would be a discovery on par with the Higgs boson, a direct window into this symmetrical layer of reality. It would not only validate supergravity, but provide a perfect candidate for the mysterious dark matter that permeates the cosmos, likely the lightest of these superpartners, stable and invisible. Yet, despite decades of searching and the incredible energies probed by the LHC, no superpartner has appeared. The elegant symmetry remains unbroken in theory but unseen in experiment. This absence is the quiet crisis at the heart of supergravity. It forces a difficult question: is the symmetry simply manifested at an energy scale far higher than we can reach, or is nature, in its infinite creativity, simply not supersymmetric in the way we have imagined? The theory stands as a monument to human ingenuity, a glimpse of a universe where matter and force are united in perfect balance, waiting for the cosmos to either confirm its vision or compel us to write a new, even more unexpected chapter. Einstein's vision of gravity as curvature may not be the only valid geometry. Teleparallel gravity offers a radical reimagining where gravity is not the bending of spacetime but its twisting. In this perfectly equivalent reformulation of general relativity, the stage of the universe is not curved. Instead, it is flat but twisted like a vast sheet that has been wrung out. The mathematical agent of this twist is called torsion, a measure of how spacetime fibers twist around each other. While curvature describes how parallel lines converge or diverge, torsion describes how they screw around one another, a fundamental geometric distinction. In this flat but twisted geometry, gravity is not a result of objects following curved paths. It emerges from a force, a real interaction mediated by a connection that possesses torsion. This force precisely mimics all the predictions of Einstein's theory, from orbiting planets to bending light, but it does so on a geometrically flat background. The potential advantage is profound for the quantum quest. General relativity, with its dynamic geometry, resists the standard techniques of quantum field theory. Teleparallel gravity, however, can be elegantly framed as a gauge theory for translations, the simple act of moving from one point to another. This places it in the same family as the other fundamental forces, like electromagnetism, which are also gauge theories. Suddenly, the path to quantizing gravity looks more familiar, potentially bypassing the mathematical nightmares that plague the curved spacetime approach. This has sparked intense interest in a popular extension known as f of t gravity, where the gravitational action depends on a function of the torsion scalar. Just as cosmologists tweak Einstein's equations to model dark energy, f of t gravity modifies the teleparallel framework. It can naturally produce an accelerating expansion of the universe without invoking a mysterious dark energy fluid, suggesting the cosmic speed up might be a signature of spacetime's torsion on the largest scales. The true frontier, however, lies in its quantum version. Researchers are actively exploring whether quantizing this translational gauge theory yields a consistent, finite description of the graviton. Could the twisting of flat spacetime be the key that finally unlocks a workable quantum gravity? translating the force that shapes galaxies into the same language used for all other particles. The universe may be whispering its deepest secrets not in curves, but in a subtle cosmic twist. The equations of quantum mechanics have always described things in the universe, but never the universe itself. That changed in the 1960s with a single, audacious equation. John Wheeler and Bryce DeWitt dared to apply the logic of quantum theory to the entire cosmos, writing down what many call the Schrödinger equation for the universe. Its solution would be the ultimate quantum object, the wave function of the universe, a mathematical expression encoding all possible states of everything that is, was, or could be. It is a staggering concept, reducing all of reality to a single, timeless probability cloud. But this monumental ambition immediately ran into a wall, one that has haunted quantum gravity ever since. In the Wheeler-DeWitt equation, time simply vanishes. The variable t, which ticks so reliably in every other quantum equation, cancels out completely. The equation describes a static, frozen reality, a cosmic photograph with no before or after. This is the infamous problem of time. If the fundamental law of quantum gravity contains no time, then where does our vivid, flowing experience of past, present, and future come from? How does change emerge from a timeless law? This paradox is not a minor technicality. It strikes at the heart of what physics is supposed to describe. The Wheeler-DeWitt equation stands as a profound warning, a demonstration that merging quantum mechanics with general relativity does not just create mathematical difficulties, it threatens to erase the very concept of change from our description of reality. Yet from this seeming failure, immense inspiration was born. The equation forced physicists to confront the nature of time head-on, asking if it is a fundamental ingredient or an emergent illusion. It became the foundational challenge that every subsequent theory had to address. For instance, the loop quantum cosmology approach to the Big Bang, which we discussed earlier, grew directly from attempts to find sensible solutions to a refined version of the Wheeler-DeWitt equation within the loop quantum gravity framework. In that model, time does not exist as a background parameter, but evolution is captured through the changing relationships between quantum geometric elements. The equation's legacy is its stark question, posed to every seeker of quantum gravity. If your theory succeeds, will it tell us what time truly is, or will it explain why time is not truly there at all? Stephen Hawking once proposed we turn time into a direction we can walk around. His approach, Euclidean quantum gravity, performs a breathtaking mathematical sleight of hand known as the Wick rotation. It replaces the familiar, flowing real time of our experience with an imaginary time coordinate, a direction that behaves exactly like a fourth dimension of space. In this transformed realm, the distinction between time and space melts away completely. The dynamic, curving history of the universe is replaced by a static, four-dimensional shape, a smooth geometrical object that can be analyzed with the powerful tools of calculus and topology. This is not just a trick, it unlocks the formidable machinery of the path integral for gravity. Instead of a single, definite history, the quantum universe is a sum over every possible four-dimensional shape that could connect an initial state to a final one. We can now calculate probabilities by, in a sense, weighing all these ghostly geometries against each other. One of the theory's greatest triumphs is its elegant derivation of black hole thermodynamics. By applying this Euclidean approach to the geometry around a black hole, Hawking found that a certain periodicity in imaginary time directly corresponds to a temperature. This mathematical necessity blossomed into the physical reality of Hawking radiation, the stunning prediction that black holes are not truly black but glow with a faint heat. The geometry itself demanded it. The framework reaches its most profound application in Hawking and James Hartle's no-boundary proposal for the origin of everything. In standard cosmology, the Big Bang is a singular boundary, a wall where physics stops. The no-boundary proposal erases that wall. It suggests the primordial universe had no beginning in time at all. In the Euclidean picture, as you go backward toward what we call the Big Bang, the time direction smoothly rounds off like the tip of a sphere or the rounded bottom of a cup. The universe becomes a closed, finite four-dimensional shape with no sharp edges, no boundary, and no need for a first cause. The question, what happened before the Big Bang, becomes as meaningless as asking what is north of the North Pole. The universe simply is a self-contained geometric whole, yet this breathtaking vision rests on a deep conceptual puzzle. What is the physical meaning of imaginary time? We do not experience it. Our consciousness, our experiments, and the entire arrow of entropy are firmly anchored in real time. Is imaginary time merely a brilliant calculational device, a mathematical bridge to answers we could not reach otherwise? Or is it a hint that our perception of time's flow is a kind of cosmic shadow, a low-energy illusion cast by a more fundamental, timeless geometry? The theory offers majestic answers but leaves us wondering if we have solved the puzzle of quantum gravity, or simply redescribed it in a language so foreign that its truth becomes beautifully, hauntingly abstract. The smooth, local geometry of Einstein's cosmos may be another grand illusion. Non-local gravity proposes that the fabric of reality is stitched together not just by the immediate curvature at a point, but by influences that reach across its entire history and structure. In Einstein's masterpiece, gravity is purely local. The curvature of spacetime at any location is determined solely by the matter and energy right there. It is a cosmic rule of immediate neighborhood influence, but what if gravity has a memory or a kind of cosmic telepathy? This is the radical heart of non-local theories, where the gravitational field at one point depends on what the field was doing everywhere else across vast stretches of space and time. The equations are modified with terms containing infinite derivatives, mathematical operations that essentially sum up the entire past and future behavior of the geometry. To visualize this, think of a still pond. In Einstein's local gravity, a dropped stone creates ripples that spread outward, affecting only the water they touch. In a non-local theory, the entire pond feels the stone's impact instantly, in a subtle, holistic way. The water's reaction depends on its entire history of stillness, a collective memory of its own surface. The motivation for such a dramatic shift is to confront the monsters in relativity's closet, singularities. The infinite density at the heart of a black hole is a sign that the local equations have broken down. Non-local gravity offers a potential escape by allowing the geometry at the singularity's location to be influenced by the same, finite geometry everywhere else. These infinite derivatives can smooth out the catastrophic spike. The result could be a black hole without a true singularity, a dense, exotic object but not an infinitely dense nonsense point. This smoothing effect might also apply to the Big Bang itself, offering another path to a non-singular beginning. Furthermore, this holistic nature of gravity could address the two greatest cosmic mysteries. The accelerated expansion we attribute to dark energy might emerge naturally from these non-local terms, as the accumulated history of the universe's expansion feeds back into its current dynamics. Similarly, the missing gravitational pull we call dark matter could be explained if galaxies are embedded in a gravitational field that is shaped by the entire cosmic web, not just their local stars. One concrete realization of this idea is infinite derivative gravity. In this model, the equations of gravity are amended with terms containing an infinite series of derivatives, making the theory explicitly non-local. These terms act like a built-in filter, suppressing the wild, short wavelength fluctuations that lead to singularities and infinities in standard quantum gravity calculations. It is as if space-time itself has a kind of elasticity or viscosity that prevents it from being crumpled into an infinitely sharp point. The promise is a theory that is both ghost-free, avoiding the instabilities of earlier massive gravity models, and potentially renormalizable, offering a path to a consistent quantum theory. Yet, this profound shift comes with profound challenges. The most glaring is causality. If gravity is non-local, can an effect precede its cause? The theories are meticulously crafted to preserve causality at the macroscopic level we observe, but the quantum implications are delicate. Ensuring that no signal, no influence can travel faster than light in this web of infinite connection is a formidable task. More practically, the mathematics of these theories is exceptionally complex. Writing down the equations is one thing. Solving them to make specific, testable predictions about things like gravitational wave signatures or the orbits of stars in galaxies is another Herculean effort. The universe, in its infinite subtlety, may indeed be woven with threads of non-local connection, but untangling that web to reveal a clear picture we can test remains the work of a generation. It asks us to consider that the force that binds the cosmos may be less like a stone creating ripples and more like an entire pond deciding together how to respond. The speed of light is the universe's ultimate constant, but what if even that bedrock principle begins to bend at the edges of reality? Rainbow gravity proposes exactly that, a world where space-time is not a single, fixed stage, but a spectrum of possibilities, its very texture shifting with the energy of the particles moving through it. This theory is a bold extension of an idea called doubly special relativity, which suggests there are two universal invariants, not just the speed of light, but also the Planck energy. To preserve both, the theory requires that the energy of a particle affects how it experiences spacetime itself. In rainbow gravity, this principle is applied to the curved geometry of Einstein's cosmos. The result is not one spacetime metric, but a continuum of them, a rainbow of geometries where each color, representing a different particle energy, sees a slightly different cosmic landscape. For a low-energy photon, the red part of the rainbow, spacetime might appear smooth and well described by Einstein's equations. But for an ultra-high-energy cosmic ray, the violet end of the spectrum, the fabric of reality would look warped, stretched, and fundamentally different. It is as if every particle in the universe is wearing a unique pair of glasses, each tinted by its own energy, and each pair reveals a distinct version of the geometry it moves through. This energy-dependent geometry has a profound consequence. It makes spacetime intrinsically fuzzy at the highest energies. As you approach the Planck scale, the differences between how particles of various energies perceive the universe become extreme. There is no single, agreed-upon reality, just a churning superposition of possible geometries. This built-in fuzziness acts as a natural, universal cutoff, preventing the infinities that plague other approaches. It directly addresses two notorious puzzles. The first is the trans-Planckian problem in cosmology. During the rapid inflation of the early universe, quantum fluctuations that eventually became galaxies were stretched from microscopic scales to cosmic sizes. In standard physics, their wavelengths would have been smaller than the Planck length, a realm where our theories break down. Rainbow gravity smears out this problem because at those unimaginably high energies, the concept of a precise wavelength loses meaning, blurred by the energy-dependent geometry. The fluctuations emerge from a fuzzy, non-singular beginning, not a mathematical infinity. The second, and perhaps more stunning, implication is for the black hole information paradox. In the standard Hawking radiation process, information seems to be lost forever as a black hole evaporates. But in the rainbow geometry near the event horizon, high-energy Hawking particles would experience a drastically different spacetime than low-energy ones. This could alter the thermal, information-scrambling nature of the radiation in a fundamental way. Some models suggest that as the black hole nears the end of its life, the rainbow geometry effects become so dominant that the event horizon itself dissolves into a fuzzy boundary, potentially allowing information trapped inside to leak out, or revealing that it was never truly trapped in the first place. The paradox may dissolve not in fire, but in a spectrum of shifting geometries where the very question of inside versus outside becomes as fluid as color in a prism. The theory paints a universe where the stage is not merely dynamic, but personally tailored to every actor upon it, suggesting that the search for a single, objective reality may be the most profound illusion of all. Every theory we have explored so far must pass a brutal test of internal logic. The black hole firewall paradox is not a new model of gravity, but a devastating argument that reveals a fatal contradiction in our current understanding. It asks a simple, terrifying question: what happens when you fall into a black hole? For nearly a century, the answer from general relativity was clear and comforting. The event horizon is not a physical wall, it is a smooth, invisible boundary. An astronaut crossing it would feel nothing unusual, a principle called local flatness. They would be peacefully, if irrevocably, pulled toward the central singularity. This is Einstein's equivalence principle in action, but quantum mechanics tells a different story. Stephen Hawking showed that black holes evaporate, slowly radiating away their mass. This Hawking radiation appears to be completely random, carrying no information about what fell in. When the black hole finally vanishes, all the information about the stars, planets, or astronauts it consumed would be lost forever. This violates a sacred rule of quantum theory called unitarity, which states that information can never be destroyed. To save unitarity, physicists propose that the information is somehow encoded in the Hawking radiation, but this leads to a shocking consequence. In 2012, a team of researchers including Ahmed Almary, Donald Marolf, Joe Pulczynski, and James Sully followed this logic to its extreme. They argued that for the information to escape, the radiation emitted just outside the horizon must be intricately entangled with the radiation that left earlier. But quantum mechanics also demands that this radiation be entangled with the partner particles that fell into the black hole. A fundamental rule, monogamy of entanglement, states that one quantum bit cannot be fully entangled with two different things. Something has to give. Their grim calculations showed that to preserve information, the delicate entanglement across the horizon must be violently severed. This break would release an immense amount of energy, transforming the event horizon from a smooth gateway into a blazing wall of high-energy particles, a literal firewall that would incinerate any infalling object. The paradox is a perfect trap. Abandon the equivalence principle and Einstein's gentle spacetime curvature breaks down at the horizon. Abandon unitarity and the bedrock of quantum mechanics shatters. The firewall presents a nightmare scenario where our two most successful theories cannot both be true in the same place. It is the ultimate stress test for any theory of quantum gravity. A true solution must explain how information escapes a black hole without creating a lethal barrier, revealing what the horizon truly is: a smooth geometric surface, a chaotic quantum processor, or something beyond our current imagination. The firewall screams that we are missing something profound, a clue hidden in the way information, entanglement, and geometry weave together at the edge of oblivion. The firewall paradox presents a nightmare with no easy escape, but one idea offers a breathtakingly elegant exit. Two of Einstein's greatest insights, once thought to be completely separate, may actually be the same phenomenon described in two different languages. This is the ER equals EPR conjecture, a proposal so profound it redefines the fabric of connection in our universe. On one side, we have ER, the Einstein-Rosen bridge, better known as a wormhole. This is a tunnel through spacetime, a shortcut connecting two distant black holes or regions of the cosmos, a purely geometric concept from general relativity. On the other side, we have EPR, named for Einstein, Podolsky, and Rosen, who first highlighted the bizarre phenomenon of quantum entanglement. This is what Einstein famously called spooky action at a distance, where two particles become linked so that measuring the state of one instantly determines the state of the other, no matter how far apart they fly. For decades, these ideas lived in separate worlds, one describing the geometry of gravity, the other describing the information of quantum mechanics. Then, physicists Juan Maldacena and Leonard Susskind made a staggering proposal. What if an Einstein-Rosen bridge and a pair of entangled particles are not just analogous but are literally the same thing? The equals sign in ER equals EPR is not a metaphor, it is a fundamental identity. A wormhole is not a tunnel you could travel through, it is the geometric manifestation of quantum entanglement itself. Imagine two entangled particles. In the quantum information description, they are linked by an invisible thread of correlation. In the gravitational description, that thread is not invisible. It is a microscopic wormhole, a stitch in the very fabric of spacetime connecting their locations. This means that every quantum connection weaves a tiny thread of geometry. Spacetime itself may be a tapestry knitted from countless threads of entanglement. Where there is no entanglement, there is no space. This turns our understanding of reality inside out. We usually think of space as the stage upon which particles interact and become entangled. ER equals EPR suggests the opposite. Particles interact and become entangled, and that process literally creates the space between them. The stage is built by the actors as they perform. This radical perspective offers a stunning potential resolution to the firewall paradox. Recall the terrible dilemma: to save information, the event horizon must become a searing wall of fire. But if entanglement and geometry are two sides of the same coin, then the entanglement between the Hawking radiation outside the black hole and the particles inside is not just a quantum link, it is a geometric bridge. The interior of the black hole and the exterior radiation are connected by a vast, complex network of microscopic wormholes. An astronaut falling in would not encounter a discontinuous firewall because the information is not lost at a sharp boundary. It is smoothly transferred through this wormhole network. There is no violent break because the entanglement is the geometry. The horizon remains smooth, not because quantum effects are ignored, but because they are the very substance of the smooth geometry. The paradox dissolves when we realize that quantum mechanics and general relativity are not arguing about the same thing from different angles. They are describing the same unified structure, one calling it information, the other calling it spacetime. The conjecture pushes us toward a grand unification where gravity is not a fundamental force, but an emergent consequence of the way quantum information is organized and connected. It paints a universe where the deepest layer of reality is not made of stuff, but of relationships, and what we call the vast, empty space between stars is actually a frozen network of quantum handshakes, a silent conversation that has built the world we see. The mathematics of particle collisions can sprawl across thousands of pages, a tangled jungle of Feynman diagrams and near-infinite calculations. Yet a stunning geometric object, the amplituhedron, cuts through that complexity with the clean slice of a higher dimensional shape. It is a jewel of pure mathematics that calculates the outcomes of particle interactions in certain quantum theories with breathtaking efficiency, bypassing the traditional framework entirely. The most radical aspect is not its power, but what it deliberately leaves out. The amplituhedron's calculations make no reference to spacetime. They do not use the concepts of particles moving from one point to another, or of cause and effect unfolding across a local geometry. Instead, the probabilities for particles to scatter and interact emerge directly from the volume of this pristine geometric form. Locality and unitarity, the twin pillars of our quantum worldview, are not inputs but outputs. They are properties that fall out of the mathematics, not assumptions built into it. This turns our understanding inside out. We have always assumed that particles exist in space and time, and that their interactions are local. The amplituhedron suggests this may be a useful story, but not the fundamental truth. Spacetime and locality could be shadows cast by a deeper, purely mathematical structure that exists prior to any notion of where or when. It hints that the universe is, at its heart, a vast geometric truth, and our experience of a sequential, located reality is a kind of cosmic projection. For now, the amplituhedron applies to simplified, toy model versions of particle physics without gravity. But its very existence is a beacon, a proof of concept that a post-spacetime formulation of physics is not only possible but potentially far more elegant. It inspires the dream of a grand amplituhedron-like object for quantum gravity, a geometric shape whose volumes encode not just particle collisions but the birth of spacetime geometry itself. The search is for a shape that does not exist within spacetime, but whose contours give rise to spacetime, offering a glimpse of a reality where physics is not about things happening in a place, but about the beautiful, inevitable consequences of mathematical form. Our universe may be a cosmic computation. The most audacious digital dream is the cellular automaton universe, a vision where reality is not a smooth continuum, but a vast, churning grid of discrete cells, each following a simple set of rules. Think of the classic game of life, a two-dimensional grid where each square or cell is either on or off. Its state in the next moment depends only on the states of its immediate neighbors according to a few basic instructions. From this minimalist beginning, astonishing complexity emerges with patterns that glide, oscillate, and even replicate. Now, scale that idea up to the fabric of existence. Proponents like computer pioneer Konrad Zuse and physicist Stephen Wolfram have suggested our cosmos is precisely such a system, a three-dimensional cellular automaton operating at the Planck scale. Each Planck-sized cell of spacetime holds a simple piece of information, a bit. The laws of physics are not fundamental. They are the emergent software, the high-level patterns that arise from the relentless clockwork updating of every cell in the cosmic grid. In this view, a particle like an electron is not a tiny ball, but a specific, stable pattern propagating across the lattice, much like a glider moves across the game of life screen. Gravity and quantum mechanics would not be separate truths, but different statistical descriptions of the underlying digital process. The probabilistic nature of quantum events could be a reflection of our ignorance of the precise microstate of the cellular automaton, just as the behavior of a gas emerges from the chaotic motion of molecules we do not track individually. It is a vision of ultimate reductionism, where the dazzling diversity of the cosmos is the output of a single, elegant algorithm. Yet this digital dream faces monumental challenges. The most severe is reconciling the discrete, grid-like structure with the smooth, continuous symmetries of Einstein's relativity. Our universe exhibits Lorentz invariance, meaning the laws of physics look the same to all observers moving at constant speed. A rigid, underlying grid would seem to pick out a preferred frame of reference, a universal chessboard that would break this sacred symmetry. A moving observer, in principle, should be able to detect the grain of the lattice, just as you can see the pixels on a screen if you look closely enough. Defenders of the idea propose clever solutions. Perhaps the grid itself is not static but dynamic and fluctuating, its effects averaging out to produce the smooth spacetime we perceive. Or maybe the rules of the automaton are crafted with such exquisite subtlety that Lorentz invariance emerges as a collective illusion, a symmetry of the large-scale behavior that is not present in the underlying code. Another major hurdle is recovering the rich, continuous mathematics of quantum field theory from a fundamentally discrete, finite system. Can a network of bits truly simulate the infinite degrees of freedom and precise symmetries of the standard model? While simple cellular automata can produce complexity, generating the exact, exquisitely tuned laws we observe is an open question of staggering difficulty. The cellular automaton universe remains a profound speculation, a hypothesis that pushes the boundary between physics and the philosophy of computation. It asks if we live not in a universe of fields and forces, but in a cosmic simulation whose source code is written in the simplest language of all, a sequence of ones and zeros ticking forward at the heart of everything. Quantum mechanics has always been haunted by its own ghosts, predictions so strange they seem to defy a coherent reality. One of the most unsettling is the transactional interpretation, a radical view that dares to take the mathematics of quantum theory literally. In this picture, every quantum event, like the detection of a photon, is not a single wave collapsing. It is a handshake across time. It begins with a particle, like an electron, sending out a retarded wave forward in time, an offer. This wave travels to a receiver, perhaps another electron. That receiver then sends an advanced wave backward in time, an acceptance. Only when this two-way transaction is completed does a definite event, like the photon being emitted or absorbed, actually occur. The advanced waves traveling from future to past are not mathematical fiction here. They are a physical necessity, weaving cause and effect into a single, timeless loop. This bizarre framework provides a stunningly intuitive explanation for the famous double-slit experiment and other quantum puzzles, but at the cost of embracing a profound, explicit non-locality in time itself. Now, a speculative leap connects this to gravity. If every particle in the universe is constantly engaged in these quantum handshakes, sending offers and acceptances rippling through spacetime, could the sum total of all these transactions create a background field, a kind of quantum static? Some theorists propose that this dense, all-pervasive network of advanced and retarded waves is not just noise, it is the substrate of reality itself. Gravity, in this view, might not be a fundamental force but a statistical consequence, an emergent tension in the fabric of these countless transactions. Matter tells spacetime how to curve, as Einstein said, but here, matter is simply a locus of intense transactional activity, and the curvature is the geometric imprint of that frenetic quantum bargaining. Alternatively, the gravitational field could be the medium that facilitates these transactions. The warping of spacetime might not just affect the paths of particles, but the very channels through which their advanced and retarded waves communicate, guiding the handshakes that build reality moment by moment. This is a theory of breathtaking ambition, attempting to ground both the non-local spookiness of quantum mechanics and the geometric certainty of gravity in a single, realist process. It paints a cosmos where every event is a collaboration between the past and the future, and the force that binds the stars is the echo of a trillion quantum deals being struck across all of time. Yet, for all its conceptual elegance, the transactional interpretation remains deeply controversial and highly speculative. The idea of physical waves traveling backward in time is anathema to our causal intuition and raises thorny philosophical questions about free will and destiny. Furthermore, constructing a precise mathematical bridge between this interpretation and the established equations of general relativity is a monumental and so far unfinished task. It stands as a testament to the lengths to which physicists will go to find a reality behind the quantum veil, proposing that the universe is not just connected, but in constant, literal conversation with itself, and that gravity may be the accent of that timeless dialogue. There is a number system so strange that even its discoverers called it the monsters of mathematics. These are the octonions, an 8-dimensional world of numbers where the familiar rules of arithmetic break down. In our daily lives, we use real numbers, a simple line. Physicists often use complex numbers, a 2-dimensional plane, to describe quantum mechanics. Octonions are the next and final step in a sequence of number systems that includes the 4-dimensional quaternions, but octonions are where the path ends and where normalcy dissolves. Here, multiplication is not only non-commutative, meaning a times b does not equal b times a, it is also non-associative. This means that if you multiply three octonions together, the result depends on which pair you multiply first. The expression a times b, then times c gives a different answer than a times b times c. It is a mathematical realm of profound and delicate beauty, a crystalline structure of exceptional symmetry that seems to whisper the secrets of the cosmos. For a small group of theoretical physicists, this whisper is a shout. They suspect the octonions are not just a curiosity, but the native language of a unified reality. The standard model of particle physics is a patchwork of symmetries, a collection of pieces that fit together but without a clear, singular reason for their particular shapes. Remarkably, the octonions contain within their 8-dimensional geometry the exact symmetry patterns that describe the forces and particles of the standard model. Researcher Cole has shown that by building physics from the ground up using octonions, the familiar cast of characters, quarks, leptons, and their forces emerges naturally from the algebra. In this framework, an electron is not a point but a specific direction in octonionic space. The different types of quarks correspond to other orientations. The forces between them are not added on, but are inherent in how these abstract directions multiply and interact. Gravity, the eternal outsider, may also find a home here. Some proposals suggest that the 10 dimensions of superstring theory, or the 11 of M theory, are not just extra spatial dimensions, but are deeply connected to the 8 dimensions of the octonions plus the dimensions of spacetime we experience. The dream is breathtaking to derive all the laws of nature, all forces and all matter, from the pure, inevitable logic of this one exotic number system. It would be a theory of everything written not in particles or strings, but in the most fundamental mathematics reality allows. Yet the chasm between this beautiful math and testable physics is vast. The non-associativity of octonions makes them incredibly difficult to work with in the dynamical, evolving equations that describe our universe. How do you build a quantum field theory, a description of change and interaction, on a foundation where the very concept of grouping operations is ambiguous? Furthermore, while the octonions elegantly encode the symmetries of the known particles, they do not yet uniquely predict their masses, the number of particle generations, or other detailed features of our specific cosmos. The mathematics is a pristine template, but our universe appears to be one very particular, and perhaps messy, instantiation of it. The octonion approach stands at the farthest frontier of theoretical physics, a siren song of ultimate unity. It asks if the universe, in all its complexity, is ultimately the shadow of an 8-dimensional crystal of pure logic, a structure so perfect that everything we see and feel is merely its broken, tangible echo. A particle can feel a force that is not there. This is the strange promise of the gravitational Aharonov-Bohm effect, a quantum whisper that gravity might leave a ghostly imprint even where it seems to vanish entirely. In the familiar world, if there is no gravitational force, an object feels nothing. But in the quantum realm, particles behave as waves, and what matters is not just force but potential, the underlying landscape of energy from which forces arise. The original Aharonov-Bohm effect, proven in the 1950s, showed this for electromagnetism. An electron beam is split and sent around a long, shielded solenoid, a coil of wire creating a magnetic field confined entirely inside it. In the region where the electron paths travel, the magnetic field is precisely zero. Yet, when the beams recombine, their quantum waves interfere, creating a pattern that depends unmistakably on the magnetic potential inside the shielded coil. The electron's phase, the rhythm of its quantum wave, has been shifted by something it never directly felt. The gravitational version proposes an exact parallel, but with gravity as the actor. Imagine a massive, rotating sphere like a dense, spinning celestial globe. According to general relativity, such an object drags spacetime around with it, an effect called frame dragging. Now picture sending a beam of quantum particles like neutrons or ultra-cold atoms and splitting it so that two paths encircle this spinning mass. In the idealized experiment, the paths are arranged so that the net gravitational force, the pull, is zero along each route. The particles feel no acceleration, yet the swirling spacetime potential created by the spinning mass should, in theory, imprint a phase shift on the quantum waves traveling the two different paths. When the beams recombine, their interference pattern would be shifted, a direct signature that the particles have sensed the gravitational potential itself, not its force. This is not just a subtle test, it is a direct probe into the heart of the quantum gravity interface. It asks how gravity, described as space-time geometry, couples to a quantum system. Does it act through the potential as the effect predicts, or through some other, more indirect means? Detecting this shift is a monumental technical challenge requiring unbelievably precise control. Experiments using neutron interferometers or atom interferometers in free fall are the leading contenders. These devices exploit the wave nature of matter, splitting a beam of particles and measuring the delicate interference fringes when they reunite. To see the gravitational Aharonov-Bohm effect, one would need to introduce a source of pure gravitational potential, like a rapidly spinning mass, and place it so its force cancels out but its potential does not, all while shielding the exquisitely sensitive quantum system from every other vibration, magnetic field, and stray particle in the universe. The payoff, however, would be historic. A positive result would provide the first clear experimental evidence that gravity couples to quantum systems in this specific, potential-based way, offering a crucial piece of the puzzle for how to quantize gravity itself. It would show that gravity leaves a quantum fingerprint even in its absence, a haunting reminder that in the subatomic world, the landscape is always more real than the force. The cosmos holds two profound mysteries that refuse to fit. We call them dark matter and dark energy, but these names are placeholders for our ignorance, labels for gravitational effects we see but cannot explain with the matter we know. The dark gravity hypothesis offers a radical alternative. What if these are not things at all but messages? Signals that our understanding of gravity itself is incomplete on the vast scales of galaxies and the universe. For over 400 years, from Newton to Einstein, our laws of gravity have been spectacularly successful, predicting the orbits of planets and the bending of starlight. Yet when we look at the outer reaches of spiral galaxies, something is wrong. The stars orbit so quickly that the visible mass of the galaxy, all its stars and gas, is far too little to hold them. According to our equations, these galaxies should fly apart. The dominant explanation for decades has been dark matter, a hypothetical, invisible substance that provides the extra gravitational glue. But despite immense efforts, no particle of dark matter has ever been directly detected. The dark gravity hypothesis asks a different question. What if there is no missing particle? What if instead gravity simply behaves differently when it becomes incredibly weak, as it is in the sparse outskirts of galaxies? This idea finds its most developed form in a class of theories called modified Newtonian dynamics, or MUND. Proposed by physicist Mordechai Milgrom in the 1980s, MUND suggests a simple modification to Newton's second law. When the acceleration due to gravity falls below an extremely tiny threshold, a scale far smaller than anything we experience on Earth, the force law changes. The modification is slight, but its effect on galactic scales is dramatic. Remarkably, with just this one new constant, MUND can accurately predict the rotation curves of a wide variety of galaxies without invoking any dark matter. It is an elegant solution that replaces an unseen substance with a tweak to a fundamental law. The challenge, however, is profound. Einstein's theory of general relativity has passed every precise test in the solar system and with binary pulsars. Any modification must reduce to Einstein's equations in those strong field regimes. while deviating only in the extreme weak field limit of galaxy edges. Building a relativistic theory that does this, one that can also explain gravitational lensing and the dynamics of galaxy clusters, has been a formidable hurdle. Some relativistic extensions of MND exist, like tensor vector scalar gravity, but they often introduce new fields and complexities. The grander hope woven into the quest for quantum gravity is that a successful theory of the microscopic fabric of spacetime will naturally produce these large-scale modifications. Perhaps the emergent nature of gravity from quantum information or the non-local effects in certain models will inherently lead to a force that strengthens just enough on galactic scales to mimic dark matter, and perhaps weakens in a specific way on cosmic scales to drive accelerated expansion, mimicking dark energy. In this vision, dark matter and dark energy are not 95% of the universe's content. They are clues telling us that gravity is not a monolithic force, but a phenomenon with different faces at different scales, all arising from a single quantum origin. The obstacles are immense. A quantum gravity theory that naturally produces MND-like behavior must also flawlessly reproduce all the successes of general relativity in our local neighborhood, a balance of breathtaking delicacy. Furthermore, observations of colliding galaxy clusters like the Bullet cluster show that the peak of gravitational lensing, which maps mass, is separated from the peak of visible matter. This is often cited as strong evidence for a separate, collisionless dark matter component. Proponents of modified gravity work to explain this within their frameworks, but it remains a significant point of tension. The dark gravity hypothesis in all its forms represents a courageous path, one that questions not what is in the universe, but how the universe itself holds together. It dares to suggest that the two greatest mysteries in cosmology are not puzzles to be solved by finding new particles, but by rewriting the oldest chapter in the book of physics, the chapter on gravity itself. Time simply vanishes from our most fundamental equations. This is the quiet crisis at the heart of the quantum gravity quest, a paradox so deep it challenges the very nature of reality. In the classical world of Newton and Einstein, time is a smooth, flowing river, an absolute stage on which the drama of the universe unfolds. But when we try to apply quantum rules to the cosmos as a whole, as in the Wheeler-DeWitt equation, that river dries up. The variable t, the symbol for time, cancels out completely. The result is a static, frozen picture, a cosmic photograph with no before or after. The fundamental law of quantum gravity seems to describe a universe where nothing ever happens. Yet here we are, immersed in the vivid, undeniable flow of moments from memory to anticipation. This is the problem of time, and any theory that claims to unify our understanding of the cosmos must solve it. The most radical interpretation is that time is a profound illusion, a trick of our limited perspective. In this timeless view, the universe just is a single, four-dimensional block where past, present, and future all coexist eternally. Our consciousness, like a spotlight, moves along this frozen structure, creating the sensation of a flowing now. But this feels deeply unsatisfying, almost like giving up on explaining change itself. A more promising path suggests time is not fundamental but emergent. It arises from the way different parts of the universe interact with each other. Think of it like a cosmic clock. If you have two isolated systems, neither has a sense of time, but if you let them interact, their states become correlated. One system's change can be used to mark the passage of the others. In this relational view, time is not a background stage. It is the story of changing relationships between things. In loop quantum gravity, for instance, there is no external time parameter. Instead, evolution is described by how the quantum geometry of space changes relative to something else, like the value of a matter field. Time is the difference between two configurations, but this still leaves a crucial piece of the puzzle, the arrow of time. Why does time flow forward? Why do we remember the past but not the future? This is where thermodynamics enters the picture. The second law states that entropy or disorder always increases in a closed system. We see an egg smash and never unsmash, ice melt in coffee but never spontaneously reform. This relentless increase in entropy gives time its irreversible direction. Some physicists, like Carlo Rovelli, propose that the thermodynamic arrow is the only real arrow. The flow we experience is our perception of the universe's journey from a highly ordered, low-entropy state at the Big Bang toward maximum disorder. Our brains, as complex thermodynamic systems, are wired to record the increase of entropy, and we call that recording the past. So a complete quantum gravity theory must do more than just recover a time variable. It must explain why the early universe was in such a special, low-entropy state to begin with. Did quantum gravitational effects at the Big Bang set this cosmic clock ticking? The problem of time forces us to confront the most intimate aspect of our existence. Is the relentless tick of seconds a fundamental feature of reality? Or is it the sound of relationships changing, of entropy increasing, of a universe remembering how to tell its own story? The answer will redefine not just physics, but our place within the timeless architecture of everything. Mathematics can build castles in the air, but only experiment can give them a foundation. The search for quantum gravity now enters its most critical phase, the hunt for its fingerprints in the real world. Our theories have painted 30 breathtaking portraits of reality, but which, if any, resembles the truth? The answer will not come from a single, monumental experiment, but from a patient, multi-pronged investigation across the cosmos and in the quietest labs on Earth. The first and oldest light in the universe holds a potential whisper from the very beginning. The cosmic microwave background, that faint afterglow of the Big Bang, is a snapshot of the infant cosmos. Within its subtle temperature variations, astronomers search for a specific pattern called B-mode polarization. This twisting, curling pattern in the light could be the imprint of primordial gravitational waves, ripples in space-time generated during a period of ultra-rapid expansion called inflation. But here is the crucial link to quantum gravity. The properties of these waves, their spectrum and amplitude, depend intimately on the physics of the universe at energy scales a trillion times higher than the Large Hadron Collider can reach. Different theories of quantum gravity predict different behaviors for spacetime at those energies. For instance, if spacetime has a foamy, discrete structure, as some theories suggest, it could leave a distinctive statistical signature on these primordial ripples, a kind of graininess etched into the fabric of the waves themselves. A future space-based observatory with sensitivity far beyond our current instruments could read this cosmic hieroglyph, telling us if the universe's first moments were smooth, churning, or woven from quantum loops. While one frontier looks to the dawn of time, another scrutinizes messengers from the most violent events in the present day. Gamma-ray bursts are the universe's most powerful explosions, sending beams of high-energy light across billions of light-years. According to some quantum gravity models, like rainbow gravity or those with a non-commutative geometry, the vacuum of space is not perfectly smooth. This spacetime grain could cause photons of different energies to travel at minutely different speeds. A high-energy gamma-ray photon might arrive at our telescopes a fraction of a second later than a lower-energy photon from the same burst, even though they began their journey simultaneously. This Lorentz invariance violation would be a direct violation of Einstein's relativity and a stunning signature of quantum spacetime structure. Telescopes like the Fermi Gamma-Ray Space Telescope are constantly monitoring these bursts, analyzing the arrival times of different colors of light with exquisite precision. So far, no convincing delay has been found, placing ever tighter constraints on how grainy spacetime can be. But with more distant, more powerful bursts, the effect could accumulate, and the next detection might finally reveal the texture of the void. The quest is not confined to the depths of space. Here on Earth, a revolution in tabletop physics is bringing quantum gravity into the laboratory. The goal is to force a massive object, one large enough to have a noticeable gravitational pull, into a quantum superposition. Imagine a tiny, mirrored sphere, smaller than a grain of sand but containing billions of atoms, held in place by lasers in an ultra-high vacuum. Using precise laser pulses, physicists aim to put this sphere into a state where it is in two slightly different locations at the same time, a quantum superposition. According to some models of semi-classical gravity, the sphere's own gravitational field should then also become entangled with its position. Measuring this gravitational entanglement would be a direct probe of how gravity couples to quantum matter, a first glimpse of the quantum gravitational interface in a controlled experiment. Other experiments seek to measure the gravitational pull between two microscopic masses, cooled to near absolute zero, to see if gravity itself behaves in a quantum way at these scales. These are not tests of a full theory of quantum gravity, but they are essential boundary probes defining the rules of engagement between the quantum world and gravity. The final frontier in this observational campaign listens to the ripples in spacetime itself. Current gravitational wave detectors like LIGO and Virgo have opened a new window on the universe, hearing the collisions of black holes and neutron stars. The next generation of observatories, both on the ground and in space, will have vastly improved sensitivity. They could hear the faint hum from the cosmic population of black holes, or even the ringing of spacetime from the moment of the Big Bang. More importantly, they will be able to perform precision tests of general relativity in the strong gravity regime like never before. Does the graviton have a tiny mass? Future detectors could measure if different frequencies of gravitational waves disperse over cosmic distances. Do black holes have a surface or a fiery firewall, or do they behave as predicted? The detailed shape of the gravitational wave signal as two black holes merge and ring down could reveal deviations from Einstein's predictions, hinting at new physics. Each chirp and ring from these cosmic collisions is a message encoded in the geometry of spacetime, and within that message may lie clues to its quantum origin. The journey through 30 theories has been a tour of human imagination at its most ambitious. We have seen space as loops, as strings, as information, and as an emergent hologram. But imagination must now meet evidence. The path forward is clear. We must listen to the universe with ever more sensitive ears, peer at it with ever sharper eyes, and probe it with ever more delicate hands. The true theory of quantum gravity, the one that describes our reality, is already written in the data streaming from distant quasars, in the ancient light of the cosmic microwave background, and in the quiet hum of a tabletop experiment. Our task is to learn its language. This breathtaking array of ideas reveals a cosmos far stranger than we ever dreamed. We have journeyed from the woven loops of space to the vibrating strings of matter, from a holographic projection on a distant screen to a universe built from cosmic Lego blocks. We have seen gravity emerge from entropy, time vanish from fundamental equations, and reality itself questioned as a digital computation or a timeless geometric shape. Each theory is a masterpiece of human imagination, a distinct answer to the same profound question: what is the deepest layer of reality? Yet, within this dazzling diversity, powerful common threads begin to shimmer into view. Discreteness appears again and again, the insistence that the smooth continuum is an illusion, that space and time are ultimately granular, built from loops, pixels, events, or nodes in a network. Non-locality weaves through them all, the haunting idea that connections transcend distance, whether through quantum entanglement, wormholes, infinite derivatives, or a fully connected primordial graph. And perhaps the most profound theme of all is the marriage of information and geometry. The universe is not made of stuff in a container, it is made of relationships. Spacetime is not a stage, it is the show, emerging from quantum bits, from holographic data, from the very act of particles becoming entangled. Gravity itself may be the thermodynamic echo of information finding its most likely arrangement. So where does this leave us standing before this gallery of cosmic possibilities? The true theory of quantum gravity is still out there, waiting to be discovered. It may be one of these 30 visions, refined and proven. It may be a breathtaking synthesis of several, or it may be something entirely new, an idea waiting in the mind of a student, an engineer, an artist, or perhaps in yours. Which of these worlds feels most true to you? Does the elegance of strings speak to you, or the minimalist logic of causal sets? Does the emergent holographic universe spark your sense of wonder, or the daring digital dream of a cellular automaton? This is not just a puzzle for physicists in ivory towers. It is a fundamental inquiry into the nature of existence itself, and it belongs to all of us. Stay curious, look up at the night sky, and remember that the darkness between the stars is not empty. It is a frontier filled with the whispers of loops, the hum of strings, and the silent computation of reality itself. The next great idea, the one that finally unveils the quantum heart of gravity, could come from anywhere. The universe has written its deepest secrets into the fabric of everything, and it is inviting